Hi everyone, I'm Nina Krasinski and I'm the Grant Science Support Coordinator for NOAA Ocean Exploration, where I support Dr. Aurora Elmore and partners at the Ocean Exploration Cooperative Institute. Thank you for joining us for today's NOAA Science Seminar. This is the first webinar in a four-part series about NOAA's Ocean Exploration Cooperative Institute, also known as OECI. Throughout the webinars, we'll meet the OECI team and hear about their exciting projects in deep sea exploration. For some general information, this presentation is being recorded and will be posted with closed captioning on this site shortly after the webinar. Today, you'll be hearing opening remarks from Adam Soule, followed by presentations from Deborah Smith, Dr. Henry Jones, and Puja Banerjee, all under the theme of preparing for the ocean data revolution. There will be time for audience questions after the presentation. You will be able to ask questions in the live YouTube chat box, but you must be signed into a YouTube account for you to do so. For those of you with a NOAA email address, in order to ask questions, you will either need to sign into YouTube using your personal email address, or you can email your questions to oeci@etal.uri.edu. It is now my pleasure to introduce Dr. Adam Soule, the Ocean Exploration Cooperative Institute Executive Director, for some welcoming remarks.
Thank you so much, Nina, and thank you to everyone who's joining the seminar virtually, and especially to our partner and sponsor in this work, NOAA Ocean Exploration. So before we jump in, I wanted to quickly describe what the Ocean Exploration Cooperative Institute is. And at its heart, it's a collection of world-class research institutions and organizations that have partnered with NOAA Ocean Exploration to help them succeed in their mission to explore the U.S. EEZ. Those partners include University of Rhode Island, Ocean Exploration Trust, Woods Hole Oceanographic Institution, University of New Hampshire, and University of Southern Mississippi. Of course, exploring the ocean in the U.S. EEZ is an enormous challenge, given that marine areas of the U.S. are collectively larger than the terrestrial portion. As a result, OECI has been able to partner with a range of organizations and institutions to help us in this mission. They include academic institutions from across the country, federal partners that have overlapping missions with the Ocean Exploration Cooperative Institute, including many different parts of NOAA, as well as commercial partners who help us meet the challenge of developing and advancing technology and scaling it up to the scope of the challenge that exploring the ocean is. We're always open for new partnerships, so if you're seeing this and are interested, please reach out and we'd be happy to talk to you. The OECI has three main mission areas. The first is operational ocean exploration. That means going out into the ocean and using vessels and vehicles to explore the ocean. Ocean exploration technology, development and advancement, and education and engagement. There is a fourth theme, ocean exploration data, and that's the topic of today's seminar, that runs throughout all of the activities of the OECI. What's fantastic for me personally about OECI is our ability to integrate across all these different mission areas that are very different. So for example, we can have a group that's developing a new piece of technology. We have the opportunity to take that out to sea, test it, find out how it fails, go back to the lab, fix it, and through all of that involve students in their training. And as we do that, we get better and better at collecting ocean exploration data. So you're going to see that kind of collaboration through the different presentations today. You're going to see about three distinct projects that have found opportunities for synergy and collaboration in order to advance each of them even further than they could have on their own. So as we talk about ocean exploration data, I wanted to mention that it's truly the legacy of our ocean exploration activities. It represents not only the new knowledge that we've created when we go out to sea, but the great potential for learning and information that extends well beyond the life of an expedition. Ocean data as you'll hear from the presenters, truly creates an ocean of data. This is a massive area. It is very sparsely explored, and simply due to its size and the volumes of data that we collect, the potential for growth in ocean data is limitless. The ocean data revolution that we'll talk about today is powered by these massive amounts of data, but it's a big challenge. It requires a whole research and development effort on its own to make that data accessible, interoperable, and useful, so that we can use that kind of ocean data to ensure the health and security of our oceans and of our nation through education, through policymaking, through scientific inquiry, through forecasting and change detection, and more. So within that grand challenge of this massive amount of data, there is a particularly difficult data type, which is subsea video. And that's going to be the focus of some of the projects you'll hear about today. The volumes that are created when you collect deep sea video are massive, making it both difficult to share and difficult to utilize. And it's a problem that's only getting more difficult as imaging technology advances from SD to HD to 4K to 8K and beyond. But I'm really excited about the progress we've been able to make within OECI, from creating foundational infrastructure to developing applications using machine learning. So without further ado, I'll let us get into the presentations. The first of our speakers today is Deb Smith, and she is the Data Governance Manager for OECI. So take it away, Deb.
Thanks, Adam. It's great to be here. So I want to talk a little bit today about these data projects, and the one that I have been working with a team of people here at OECI primarily on is video, like Adam said. But if we take a step back and look a little bit about the volume of data that OECI is collecting over the last 5 years, we have participated in over 46 expeditions, which equates to about 721 days at sea. And that includes 142 ROV deployments. And with that, obviously, you can see on the right, there is a huge amount of data, 380 terabytes of just video data compared to the 15 terabytes of potential other ship data, whether that's multi-beam or imagery or acoustics, different stuff. So that's 25 times the size of the basic ship data that we're now trying to take on that fire hose and work with. And so the project at OECI that we've been working on is making that video data accessible both to the public, but then potentially accessible in the future to be able to work with that video data. And the uniqueness about video data is that there are many, many uses for it. You know, one of the things that is most challenging is that, you know, you might have a biologist looking for a specific creature, kind of like the octopus to my other side. Or you might have a geologist looking to see what type of sediment as the ROV is going by. And so you'll hear a little bit later about a project that might be able to help with the volume. One of the other projects we have been working with a team here at University of Rhode Island is making the video data accessible for people to play on YouTube. And so if you go to YouTube, you can actually play full dives from the Nautilus. And there's a new function that allows you to sort of search for or look for a particular type of thing within the video. And so this is a great program where you can actually click on the links of the time and it will take you straight to the thing you're looking for. And so that just makes it a little bit more accessible for people to try to find the things that they want to review without having to watch hundreds and hundreds of hours of video. One of the kind of bits of math or data that I looked up for this presentation was that if we had one person to review all of the data that we've collected in just the last 5 years on the EV Nautilus, it would take somebody 428 days doing 8 hours of review to look at all of it. And that might be for one thing. And so obviously there is lots of different reasons why you might want to search for something in video. And you'll hear about a project a little bit later from Puja that talks about, you know, scaling down the video and then being able to kind of search through some of that. The other project that we're working on is putting this video data into the NCEI's video data portal. So OECI is funded by NOAA's Office of Ocean Exploration, and their ship, the Oceanus Explorer, hosts their data up at NCEI on the Ocean Exploration video portal. And you can access this. It's publicly available. You can play and watch their video clips. And we're working right now on the pipeline to be able to put the data from OECI there as well. And so this will give people an opportunity to be able to look through and search for particular things within the event notes, and then the user can play or download the video from there. And so this just also allows us to have a greater flexibility in providing that. The layer of R&D on top of that project is this AquaView. So if you think about, wouldn't it be great for all this data just to live in the cloud? Well, there's challenges with that. One, how do you find it? How do you create a list that you want to run a machine learning algorithm on? How do you even know what's out there and available? And so this AquaView platform will actually allow you to search through and find the data and then actually run other programs on it. And this is something we are just started looking at because there's huge cost impacts to that, both the volume and the size of the data storage, but also every time you access those data and try to run an algorithm, the cost just gets exponential and exponential. And so we're working on trying to figure out ways to work with NOAA and ways that we can potentially streamline that work and also allow users to be able to kind of create programs that will allow you to quickly look through and find the bits of the video that you need to use. So that's what we're working on here at OCI. There are lots of other data projects as well, but this is a snapshot of what we're working on right now with video. And I'll send it back to Adam.
Thanks, Deb. That was fantastic. Can't wait till all of that is in action and we can find the video more easily. It's my pleasure now to introduce Dr. Henry Jones, Director of Research and Development and Scientific Entrepreneurship at one of the OECI affiliate organizations, University of Southern Mississippi, who's going to share with us the work that he's been doing on infrastructure for ocean exploration data. So take it away, Henry.
Thank you, Adam. I have been looking forward to this. For an audience like this one from so many different backgrounds, to talk about a relatively mysterious topic like infrastructure for ocean exploration data, I found that it helps to start by getting everyone on the same page. Literally, in this case, a map page. I won't ask for a virtual show of hands, but depending on your age, this photo likely brings back some bad memories. Wasn't all that long ago, if you were driving somewhere, it looked like this, with no way to know for sure where you were or if you were on the right path to get there. I know the family fights that we used to have about whether to stop and ask directions or not, and then the exasperation when we found out, yes, we should have stopped and asked for directions because we made a wrong turn 3 hours ago. That was not good for family bonding on our trips. But then came online maps, where at least the information was recent and you had a sense that you were being smart about your route. But nonetheless, these maps were created by map companies and were in many ways still basically the same as paper maps. But the transformational jump happened when maps went mobile, and that has changed everything about getting from point A to point B. And a similar transformation is what we're aiming for with our infrastructure for ocean exploration data. What happened is, along the way, something very important and revolutionary happened. The users of the maps started adding to the maps. And at first, it was what we would call annotations back then when we were adding these to these maps. And it's exactly what you just saw in the presentation that Deb gave and the text content that's associated with the video. This is a big deal. Being able to put additional insights about big groups of information. And in this case, it was done by the drivers themselves. So turning every data consumer into a possible data producer, that was the big deal. And you'll hear even more about the latest in annotations and working with this super valuable but difficult data set of video in the next talk. But the good news is for us who were driving, it didn't stop there. Because of this new two-way data infrastructure that was built for far more than just getting a map into your hands, this information was collected and sent up automatically by the computers themselves. So there was no person involved. The computers did our work for us. Our smartphones that were using the maps started sending information to contribute to the maps. And the result, like you're seeing on the screen here with these the red, the yellow, the green that really impacts the way that we think these days. None of us would want to not have this access to real-time traffic. I mean, we used to have rush hour traffic helicopters to help with this sort of thing, and they're totally gone now. I don't know how many people, remember those, but there's no need for them now because we are all data producers and much less expensive way to get that information. But what's cool is that more than just a snapshot, the helicopters would just say Interstate 101 is a standstill today at University Avenue. That's all we had to work with. All this data can be saved across months and years. So we have trends. We can do all sorts of analysis. We can inform our government how to improve our road infrastructure. We can help businesses decide where to go, where they're going to invest. And what started as better paper maps has become the foundation for what was once total science fiction, the self-driving vehicles that were happening today. And possibly, most importantly, it's significantly reduced the stress on our family road trips. Okay, so hopefully now we're all on the same page about how widespread access to data and being able to collect data from the consumers so that they're also producers can get us from paper to science fiction. So I've got another map to show for you. Why this map? Because as far as underwater maps go, in terms of our road driving maps, this is about where we are today. As of 2023, 24.9% of the seafloor has been mapped using relatively high resolution technology. Coverage for detecting objects like gas seeps or missing airplane wreckage or any other real detail is less than 1%. And then what about the water itself? The salinity, the temperature, the current, environmental DNA, all of that's in between the surface and the seafloor, and it's always changing. And according to NOAA Ocean Exploration, only about 5% of the world's ocean has been explored, leaving 95% unknown. So we don't know how to answer really what life is underway within our oceans. How's it changing every day, every month, every year? What are we missing? What should we be doing differently? And video, as you just heard from Deb, is full of those data to help us with those answers. But how do we cope with so much of it? How do we go from the map that's mostly, as you saw, a lot of mystery and blank space to that equivalent of the real-time lines of green and yellow and red roads data that give us insights so we can make daily smart decisions? Well, it won't be the old way with ships and crews. It's going to be with uncrewed systems. And there's a lot of uncrewed systems, which is really great because the ocean is a very complex environment, and that requires a diversity of explorers. The flip side is that we have a lot of data headed our way, as you heard about from Adam in the introduction, to fill in all those blanks. I mean, a lot. So we are quickly getting to the point where each year we'll be capturing far more ocean data than all the ocean data we've captured so far in human history. And then we'll be capturing that much per month and then per week. It's a lot of data. And if that weren't enough, at the same time that we were having this data explosion, we're having a computational and algorithmic explosion, today's artificial intelligence wave. And these AI algorithms, they are relentless data consumers, and they will fully stress any infrastructure that it's using. It'll find the weak points. If there's enough storage, it'll max it out. Enough compute power, it'll max it out, or until it just maxes out the network itself. One AI science algorithm working on a problem can be hungrier for data and computation than all of the human scientists working on the problem. And it'll be more productive than all of them too, because it's working 24/7, 365. So if we are smart about it, this AI explosion can enable a science explosion. But we do have a fundamental problem. Our current infrastructure is not built for this. Just finding data, like in this video here of a current system, is not much better than looking through a card catalog. It's not automated, it's not easy, and it's unfortunately not always reliable. In this example, after all the searching, the actual data has been moved and can't be found. This is not the setup that we are looking for the future, that we must have for the future. And that future is arriving quickly. You'll be seeing some AI generated images as I wrap up this talk that were not even possible a year ago. And that's bringing us now to our uncrewed systems data assembly hub, this data infrastructure we're building by looking ahead. So I'm going to geek out for a minute about what that means behind the scenes. So if there are any fellow geeks on the talk attending the seminar and you want to know more, please contact me. So one thing that we're doing is we're building a system that's scalable. It's designed for federated, not centralized data. Like Deb showed, the video and the annotations, they can stay at YouTube, for example. They can be at the video data portal. They do not need to be all pulled into one spot, which is crucial for the amount of data that we're talking about. It's flexible, so we're using a NoSQL database for handling the metadata because there's all sorts of stuff in the future that we just, by definition can't expect. We're using the insights from NOAA and the Navy, who are global experts in uncrewed systems for the metadata schema structure. We are using large language model tools for including new data. These are new things for all of us to figure out how to use, and what we've seen is that it's great for not just for the collected stuff that's now coming in, but also the historical data, like all the in the warehouse for Indiana Jones and the Temple of Doom. It's been too expensive to go through that manually, but we can put an AI agent to work and it will go through and get all of that and bring it back into something that we can put to use. And it's extensible. So like with my earlier mobile maps example, the Data Assembly Hub embraces annotations and analysis as data and is prepared for all these new data producers as our AI scientists grow. So now you'll see a video with a few aspects of the Data Assembly Hub in use. Like a lot of infrastructure, this is not too sexy in and of itself. We're still early on. We're enabling the science fiction that's yet to come. But what's important here is that while you're seeing a human click through a website, it's all built for automated searching and access with APIs, application programming interfaces. So instead of looking for a particular set of data, the hub takes a request for an area or a time frame or both, and then finds everything available in whatever format, including video, images, annotations, analysis, contributed by others, all of that treated the same. And then the hub will also recommend data to you based on what you've asked for, what others have asked for, what's available, and then packages it all up into a familiar cart. So this is the infrastructure that we are building for the labs of the future, where the creativity of each scientist is multiplied by many, many AI assistants. And the Data Assembly Hub, we're designing it so that discoveries can be uncovered and utilized quickly so that the lab and the ocean ideally can become figuratively and literally intertwined. And far more of the world's oceans are able to be understood, appreciated, and valued. So with all that said, if something about the last few minutes has resonated with you, please contact me or my colleague, Josh Hill, who's the technical lead for this project. We are really looking forward to any questions. And with that, I'll go back to Adam.
Thank you so much, Henry. That was fantastic, and really appreciate your efforts to bring the future to now, and it's very exciting. So our last presentation, we get to see a project that developed one of those artificial intelligence agents. This is a presentation by Puja Banerjee, who's a Ph.D. student here at University of Rhode Island, supported by the Ocean Exploration Cooperative Institute. She's going to be talking about her project Rovia, and she won't want me to say it, but she's nearing the end of her PhD for those of you looking for a fantastic ocean data expert to come join your team. Take it away, Puja.
Thank you, Dr. Soule, for the introduction. So today, as we all are talking about the big data revolution, and I think this point has already been stressed enough that large volumes of various data sets are being collected as a part of ocean exploration. And just like Deb already showed you the statistics, they are really voluminous. And it's a real big challenge to organize and archive and manage those data sets. So especially when we are talking about deep sea multimedia data sets, such as videos, which are collected by underwater robots, such as AOVs or ROVs, these videos are sparse And by sparse, what I mean is that, as you can see on your screen, there are only certain parts of those videos which is really interesting. So these long ROV videos, they run for hours and hours, and they create large volumes of extensive data sets. However, if you carefully go into these videos, you'll see that when the camera, the underwater ROV, is scanning through the seafloor, there are only certain sections of those videos where it finds something interesting that could be a potential subject of interest. For example, here I'm showing a coral. So the ROV stops and gradually zooms into it so that it could record more features associated with it. And that's where we find the importance of highlights or short clips that are being extracted from these ROV videos. So till now, humans have been annotating this manually. So basically, we have been spending hours, days, and months sitting on the desk and finding out those short clips known as highlights, which could be used not only for our research or scientific purposes, but also for communicating science to the public, just like what we are doing today here. Therefore, while everything is getting automated around us, we thought, why not use artificial intelligence and develop a tool that can perform that task for us? And that's where I would like to introduce Rovia, which is basically a tool that we have built by utilizing the concepts of AI, which can generate the deep sea video highlights automatically for us. So the science that has been used behind the development of this algorithm is basically by applying the concept of optical flow, which is basically, you can imagine, it is able to extract the motion in a frame. So, for example, when somebody crosses the red light at the traffic signal point, or if there is detected some kind of motion in our security cameras, ring cameras, when someone passes in front of it, is exactly the same concept that we have applied here, just because the camera, most of the times, as I've mentioned in my previous slide, that it generally stops and gradually zooms in so that it could capture more information about the subject of interest that it's focusing on. So here, that the concept that we have developed by utilizing the science of optical flow is basically GRAMA. And just to give you some idea, here is a cool video clip, which is where it's manually identified as a highlight. So here it is. So as you can see, the camera gradually zoomed in into this fish, which is like actively flapping its fins. And as you can see, these arrows are basically, the vectors are basically recording the motion and extracting that information from this clip, which is creating a divergent field as it zoomed in. Basically, the arrows are pointing outwards, and gradually you'll see when the camera will zoom out. Yeah, here it is. So the vectors are pointing towards it. That's it's basically a convergent field. So you can imagine it like a breathing flood that is opening and closing slowly. So we have utilized that original video and converted it into grayscale, just because we have seen in the deep sea environment, we really don't see the accentuated red, green, blue colors. And it was important for us to reduce the computational burden to create this model. So we converted them into grayscale. And then by applying the concept of optical flow, you can see here how the magnitude and angle information is being extracted from this video as the fish is actively moving. So this is what we have conceptualized this whole idea as GRAMA. Now here is another video. If you see here where the fish is not moving. So for example, like the previous example where I gave you a clip of that coral that was not moving, still the machine was able to identify this as a highlight. And how it is able to extract that information is by the same applying the concept of GRAMA, where the vectors are still moving because the camera zoomed in, even if the fish is like maybe taking a nap, that too with wide open eyes. So you can imagine there is a kind of relative motion that's being played between that potential subject of interest and then the camera. And this is how the machine is exactly utilizing and this information and extracting this information so that it can train itself for similar kind of lots and lots of other such examples, and knows that, okay, this is what a potential highlight would look like in most of the videos. So this is where Rovia has been successful, and it has been field tested last summer, where it was automatically able to generate highlights for such long RV videos. So Rovia is now available online. It is being uploaded on GitHub. And as you can see here on the screen, there is a full manual, and you can follow this manual and download it on your personal PC. And it's compatible both with both on Windows as well as Mac. So you can just follow this manual and follow the steps and install it on your computer. It's a portable, very easy to follow tool that we have developed so that anybody can just download it and run it on their PC. So here is a quick demo where I have been running it on my own screen, just following the steps, where there is a full directory of long video RV videos that were like newly collected, and the machine or the algorithm didn't see it before. So we run this algorithm, the Rovia model, and as you can see, slowly it will read all these videos and then go through it, and then there will be a full directory of highlights that it will be able to extract and produce it just within few minutes. So it's basically like the things what we have been doing manually, sitting on desk for hours and hours, the machine just does that automatically, and you don't even need to sit on your desk. Just run the algorithm, and the directory will be created where, as you can see here, Rovia clips is basically the folder where all the highlights will be stored. So that's all about Rovia. So it has been a very efficient tool, and I can say that 82% of the times it has been able to correctly, that is the precision level that we have achieved until now with all the videos that we have trained, that we have used to train our AI model. And 94% of the times it was able to correctly identify these highlights. So yeah, that's all I can say about Rovia. And it's one of its new kind of tool that has been developed using the concepts of deep learning AI. So please give it a shot, and we would definitely like to hear some feedback if you are, or any troubleshooting problems if you come across that while running it on your PC. And thank you for everyone who's attending this talk today. So over to you, Dr. Soule.
Thanks, Puja. That was fantastic. And thank you to all the presenters. We saw, Puja just described a tool that she developed. Henry described the infrastructure that might allow you to apply that tool, and Deb described how we make this data available. So really appreciate everyone's contribution. We have an opportunity now for some questions from the audience. As Nina said, you can enter them into the YouTube chat. Otherwise, we can, I have a few questions that I'd like to ask as well. In fact, we did have one question come in from EV Nautilus, where there's a watch party for this seminar. And they asked, what is the coolest discovery that has been enabled by being able to look at this big data? And I might expand that to say, what are the potential discoveries that are still to be made, since all of these approaches are more in the prototype and developmental stage. So let me shoot that over to Henry, if you want to comment on what you think some of the kind of discoveries that we can potentially make from having access to all this data?
Yeah, so one of the things one of the reasons I like to be a data scientist is when the data surprises me completely, and when there are features that come out, or there are patterns that we can see that are the result of having the data we didn't have before, and then the tools to go process that data once we've got it, and especially if we can use tools like Puja has created to do it automatically. And so you try it one way and it runs, and you try it another way and it runs, and instead of being completely exhausted from the hours that you spent at your desk, you are inspired by the results that you're seeing from those results. And so what I'm excited about are the things, it's a little bit enigmatic. I'm excited about the things we don't know about yet. But those come about because of these tools that we're able to put in place. So an example might be that using some of Puja's tools to look for certain things in particular, often there are errors that are rejected from a data set that when you look at them, you discover they are actually the signal for some other thing that you didn't know to look for. And that's really impossible to do manually, but it often comes out of automated processes.
Very cool. I have a question is there any place where I can access, or where can I access the data that gets created by the OECI? I'm going to shoot that one over to Deb.
Yeah, there's a number of public repositories that OECI uses. Specifically, the Nautilus data is available, both the shipboard data at the rolling deck to repository, so R2R. The data also goes from there to our National Archive, NCEI. They also archive their data at MGDS, which is most of the vehicle data, ROV vehicle data, like the reports and the images and things like that. And you can find the video data currently right now on YouTube. And like we said earlier, we're looking to put that in other places. And other projects within the OECI, some of it is hosted at the institutions. So you can look at various repositories at Soule or UNH and USM and URI. But typically there's a link from the major. And we typically archive data collected at sea or environmental data. So those are the primary types of data that we're putting into these archives and making publicly available.
Excellent. We got a question coming in for Puja. Have you considered using the audio that goes along with the video in producing video highlights or clips?
Yeah, that's a wonderful question. So we have seen, like in most of the cases, the audio gives us a lot of information while creating the highlights. For example, if you consider a sports video, when there is a loud noise in the audience when somebody just scores a point, so that has been really useful in videos such as like sports videos. But in our case, when we are trying to analyze these oceanic data sets, we really don't hear anything other than the ship noise in the deep sea. There are basically comments or chats that's going on board between the scientists describing about those potential subject of interest that they're focusing on. But there is also some other chats or conversations that's like going on whenever there is when the camera just scans through the seafloor and there's basically nothing important in the frame. So in our case, we saw that that's giving us false highlights. So yeah, till now, we have not been able to utilize that audio data set for this purpose of creating highlights, but that's a really cool thing if we can use it later on in future. Yeah.
Excellent. That's cool. Question is come in, what is the long-term plan for the data assembly hub? So I guess I'll fire that over to Henry.
All right. So we've been working on this for a couple of years, and already we found quite a few places where it makes a big difference. It just turns out that most ocean scientists don't really want to be data scientists, and these days you got to be a little bit of a data scientist. So we are trying to take that burden off of the people who don't want to do it, because that's really what we love to do. And so consequently, we've been working with NOAA's Research Operations Transition Office. But along those lines, we are seeking beta testers for the hub. So if you are a producer of data, if you're a consumer of data, and in particular, if you are a consumer of data who would like to be also a producer of data, like I was speaking about earlier, we would absolutely like to talk to you about that.
While I have you, Henry, Puja just mentioned some of the cues that she's been able to take from sports video highlights. I'm wondering, in your creation of the data assembly hub, what other domains are doing the same thing that you're able to learn from?
Yeah, that is a really great question, because I think we are all surrounded by a lot of video these days. Early on in our project, we got a lot of insight from the Department of Defense, because they had been working with georeferenced video for quite a while and had spent billions of dollars trying to work with that better. But frankly, in the intervening years, YouTube and Netflix, who also handle a whole lot of data, they are also, they put into place their recommendation engines, which is something that would be very useful for science, and also preloading data. Also another very useful tool for data science and for working with the data sets. And so consequently now it's Amazon, Microsoft, Google, the cloud services providers. They are having their own answer set for some of these, and we're able to put those their tools to use for our particular application. And just one last little bit, these days the AI companies who are really rapacious data consumers for their models, things like retrieval augmented generation, phrases that didn't make sense to anybody 2 years ago, are now really important concepts to understand that we are putting into place for the data assembly hub.
Excellent. We've had a couple questions come in about Rovia. The first, Puja, is viewer asked, can Rovia detect plumes or oil leaks? And then another was, have you tried to license this AI tool? Can you respond to those?
Yeah. Okay, so I will start by the first question. So Rovia can detect plumes or oil leaks just in case, like I have mentioned in while explaining about Rovia, how that algorithm has been built, that if the ROV or the underwater robot actually stopped and zoomed in while for detecting that plume or the oil leak, then definitely it has been registered in that model, because the camera stopped. There has been a change in the velocity or the motion of the camera and that related field. So definitely it will be automatically able to detect that plume or oil leaks if the camera stopped in there. If not, until now, we have not trained Rovia with certain that kind of examples. But if we train it with certain such examples where maybe the camera didn't zoom in, it just went by, but there was something like that was potentially important, for example, then it will be able to definitely detect it automatically with Rovia.
Yeah, I would assume that using the same approach, that a gas leak or an oil plume would produce motion that is kind of directed in the imagery. What about licensing? Have you tried to license this tool?
Yeah, so I think we get that question quite a lot. So yeah, we are in process. So let's see. But yeah, we are in process to license it so that it can be a full OECI patented stuff that can be used by the federal government, or even for you can use it on your own personal PC. But yeah, we are in process of doing that.
Cool. A question has come in that asks whether any of these projects can potentially contribute to finding marine debris such as microplastics. I'm going to let Deb handle that, who has a kind of good finger on all the data that's collected and whether any of it is could be valuable for marine debris.
Yeah, I think that, there's lots of types of data that look for marine debris, but most significantly, I think people are one of them. But we do some science research, water filtering. So CTDs and water filtering and things that look for microplastics in the actual water, but also looking for marine debris and large things. One of the things we do look for in underwater footage are those impacts to the seafloor. And those are typically noted in the video event logs. But yeah, there's a various scale of different ways to look for basically our human impact into the ocean.
Nice. Question for Puja again. People want to know how long it would take Rovia to generate highlight clips from a full dive, say 10 to 12 hours of footage.
Okay, yeah, that's a very good question. So if you have enough memory on your PC, if you're running it on not on supercomputer, but on your own PC, I would say it would take maybe 2 to 3 hours for a 12-hour long video to generate that highlight. And if you're looking at, we actually tried it on much shorter video format during our last expedition last summer. And for half an hour video, it just took 7 to 8 minutes to create those highlights. So it was pretty fast, I would say. So yeah, just give it a shot if you have memory and you can just run it on your computer and let us know that how much time it took for you.
Thanks, Puja. Henry, you mentioned in your presentation that there are many different uncrewed systems used for ocean exploration. Do they all serve the same purpose, or do they differ in some ways? And I guess maybe to add on to that question a bit, what sort of challenges does that create when you're trying to assemble the data from these different systems?
Yeah, that is a really good question, Adam, and a core part of the challenge and the opportunity, really. It is, the ocean is a very complex space, and so we need a diversity of explorers. But that means that not only is each platform going to be different, but it's very common for the dives for a given platform to change from dive to dive, and we want that to be the case. We want to make the most out of every bit of effort that takes place, and where some of the past ways to collect data are pretty set. If we put a satellite into space, we're not putting a new sensor on it anytime soon. It's going to be the same data coming down day after day. But with underwater systems, especially the uncrewed systems, it'll be different just through the course of a single day. And that's where metadata is so important. It's a term that if you're not in this world, you probably don't know what it means. And if you are in this world, it's one of the most important words that you have to work with every day. And what that metadata does is it describes what's there on the platform, where was the platform, when was the platform doing its thing, what sensors were there, what were the settings for the sensor. There's a lot of information to make the data sensible that must be somewhere, and the metadata is where that is. And so handling a lot of different types of metadata becomes a really big part of the problem to solve.
Thanks, Henry. Well, I'm going to start wrapping it up. I really appreciate everyone who presented and who attended. And I think that the message came through really clearly today that, the ocean data revolution is about exploring the data we produced while we were exploring, that collecting data and putting on a shelf is not doing a service to the efforts of all the people who went out to collect that data. We can extract much more information and knowledge from it, and we're building the tools to help do that. So thank you very much, and please reach out to OECI or to any of the presenters today to learn more about what we're doing, and we'll see you at the next seminar.
All right, thanks, Dr. Soule. On behalf of all of our guests today, I would like to thank you very much for joining us to learn more about the Ocean Exploration Cooperative Institute. I would also like to thank all of our OECI partners and NOAA collaborators who make all this work possible, especially the University of Rhode Island's Interspace Center, who produced this webinar today. As I mentioned earlier, this webinar is the first in a 4-part series highlighting the amazing work of OECI. Details on the upcoming webinars can be found using the QR code on your screen. And I hope that you will join us this Tuesday, August 27th at 2 p.m. Eastern Time for our next webinar on midwater exploration through multi-vehicle operations. It will be hosted by OECI partners from the University of Rhode Island, Soule Oceanographic Institution, and the University of New Hampshire. This seminar will also include a live interaction with OECI members aboard the AV Atlas. Thanks for joining us today, and we hope to see you next time.